Hello. Good morning, Amin. Good morning, Nukas. And good morning, D. Stratus. Hi, Mike. Hello, Pika Pika, Jebukati, and Shrek from the swamp. What's up, Brandon? And that guy who stinks. Good morning, Belkit. Jack, there is not a handout today. We're doing it live. Hey, Antonio. Thanks for sending me that animation, by the way. That was really cool. I haven't gone through the ant simulations yet, but I watched that double pendulum. Hey, good morning, H. Swan, Jimolino. Dang it, we're doing it live! That's right, we're doing it live. Happy Wednesday to you all. The ant ones are pretty cool. I got it to make a little USA map using a MathWorks example. Hello, Kate. Jibukati says, for number 3 on the homework, are there notes on the estimator gain matrix? Yes, as of Monday. Wait, Antonio, what's going on here? What does it say? Pheromone deposits. Are these ants traveling all over the world? I mean, all over the states. The darker the colors, the more confident the path is. So we have something, what is, oh, my geography is so bad. This is like New York, right? Somewhere in New York, and this is maybe in Florida. This is somewhere in like Montana, somewhere in California. We're very confident about these paths. It converges right at the end. I have 12,000 unread. Look, people have different ways of managing inboxes. Because I mean, if you like get rid of every email, like that's a lot of work. You know, do you guys actually clean up your inboxes all the way? It's a lot of work. Okay, hold on. Let's get started. It's just random points in the US. I didn't pick anything specifically, LOL. Oh, great. And here I was thinking those should be cities that I know. Hello, Adam, all together. All right, everybody. Today, we're going to do a little simulation building off of some code that we have made before. So this is what we were talking about last time. We're going to make a simulation of this cart pendulum system. We're trying to balance it. We're trying to control it so it stays upright. And we got to the point where, I mean, we have a model for the dynamics, and we have a feedback controller that we're going to use. But we talked about the problem where you need to be able to estimate your states. Oh, geez. Yeah, I forgot about the music. Thank you, Pika. Oopsies. So we have this prediction state estimator because our control input depends on estimating the states. And this is called the Leunberger Estimator. This equation right here, where x hat, this vector, is your state estimate at a given time. And it depends on the measurement prediction error. So this is the difference between your estimated sensor output and your measured sensor output. And we multiply that measurement prediction error by the estimator gain matrix. And you choose this matrix, or you calculate it depending on how quickly you want your estimated states to converge to the true states. So we went through a little example here. Let's see. Let's go down a little bit. So how fast do you want your estimated states to converge to the true states? Well, there's at least one rule of thumb. The settling time for your estimator should be 2 to 6 times faster than the settling time of your controller. So our controller, we want it to balance itself in around 1 second. So I chose, let's have our estimator get those states that we need in like 1/3 of a second. And we also further specified, hey, why don't we have 20% overshoot on there? So the reason I even put an overshoot condition is with the combination of overshoot and this 1/3 second settling time, I could just come up with a pair of complex conjugate roots that look like this. I mean, I could have also picked just one real root for the estimator. Because you can just pick a root on the real axis that converges in 1/3 of a second. So it's just kind of whatever you pick. You have to pick some dynamics for this, and this is just, it just happens to be what I picked. So if I want this to be the dynamics of my estimator, this matrix, A minus LC, is like the system matrix for the estimator. So like we have a closed loop dynamics matrix for the overall system, you have a closed loop matrix for your estimator. And so you have to calculate L so that the eigenvalues of this matrix are equal to this. I know I'm quickly blasting through this. I know this is all very fresh, so I don't expect this to have totally sunk in yet. But anyways, we came up with this equation at the end. This equation, you could call it the Ockerman Equation, or the estimator Ackermann Equation. So in state feedback controls, we end up using these types of equations keep coming up over and over again. So we call it an Ockerman equation, and it's always solving for some matrix related to your control system performance. So this is the estimator matrix that we are going to use. And so now we're going to go into MATLAB and start working on a simulation. So if you have is this the one that I want? It's a cart pendulum. No, I think it is this one. Wait. Cart pendulum. We were doing one in class. Yeah, this one. Carl says, does that mean we can use the Ackermann formula in MATLAB to solve for L? Yes. Ooh. That's something I wanted to show you. And so we might as well do it right now because you have asked about it. Okay. Let me show you this. So I'm going to copy this equation really quick. And I'm going to bring it over to a new clean area. So let's paste this in. So this right here, like we said, this is our estimator Ackermann equation. But I want to pull up the Ackermann equation for the controller really quick. So let's walk back down memory lane. The controller Ackermann equation for this same system, it looked something like this. Actually, I'll go back to using black. Our feedback gain matrix was equal to 0, 1 times our controllability matrix. You take the inverse of this, and then we had this characteristic equation on this side. 52a plus 0.67 times the identity matrix, which was 2 by 2. So if you compare these two, they look very similar but kind of flipped. And I'll just point this out one more time. This BAB, we call it C. This is the controllability matrix. You have to be able to invert this matrix for your system to be controllable. So it's like a check you can do in advance before you even try to design a controller to be like, can I actually control this thing? And then this matrix is the observability matrix. And I like to call this like O, capital O with a curly thing. So just like the controllability matrix, you have to be able to invert the observability matrix in order to be able to solve for L. And so that means the observability matrix must be invertible in order for you to be able to estimate your states. So transpose or inverse. Oh, I think you're saying like these are looking like the transpose of each other. Yeah. So this is something you should also check. Can I invert my observability matrix? Because if I can't, I'm not going to be able to estimate my states. And if I can't do that, then I can't give my state estimates to the controller because the control input at a given time step is minus this gain matrix times my estimated states. So whenever you see a hat, that means an estimate. So actually everything's tied together. Like your system needs to be observable and controllable. If it's not controllable, you can't solve for this matrix. If it's not observable, you can't estimate your states. So if you're not observable, then you can't do that. If you're not controllable, you can't do that. So either way, it makes it so that you can't design a state feedback controller. Okay, so now, so let's talk about the Ockerman equation. We know in MATLAB, to solve for k, what I can do, I can say k, and then I use the Ocker command, and I put A, B, and then I put my vector of desired closed loop poles. All right. And this formula in MATLAB executes this calculation up above. So this is much faster to use than to write out all those equations. So Carl was asking, can we do the same thing with this? Because we called it an Ockerman equation. All right. So the answer is yes, but you have to kind of trick it into working. So what I want to do to show how this works is I'm going to name this matrix out in front. Just for simplicity, I'm going to call it X. I'm going to condense it to X. This matrix on the right-hand side, let's just call it Y. And then for this, we already have a symbol for this. This is the observability matrix. So let's just call it observability inverse, because that's the inverse of the observability matrix. So I'm going to use these same symbols and rewrite this equation down below. So I'm going to say L is equal to matrix X times the observability inverse times something Y. So those just represent some larger matrices. Okay, here's some linear algebra, some little nice tidbits that you may or may not know. What if we take the transpose of this? Okay. So now I have to take the transpose of the right-hand side. All right. Take the transpose of both sides. So here's a little linear algebra info. The transpose of this stuff on the right-hand side, you could write it as Y transpose. So you bring that rightmost matrix over times the transpose of those first two terms. So it's kind of like you switch them. So this goes back to the principle of like AB transpose is B transpose A transpose. So I'm basically using that property here, but I'm calling this A and I'm calling this, oh wait, no. I'm calling this A and I'm calling that product of two matrices B. And then I'm just using this property and that's how it turns out. You can use this property one more time again on this matrix. So you could call like this A and this B like a new set or something. Maybe just to distinguish it, we'll call it like A prime and B prime. So you apply that rule one more time and you get Y transpose times the observability matrix. Isn't it B equals Y and A equals X naught? Wait. So I have A, B transpose is B transpose, A transpose. I think you're right, Kate. Wait, so I'm calling A... Yeah, because I'm getting A transpose over here, so A should be... Okay, I'm calling this A, and I'm calling this B. Thank you, Kate. And now it'll match up. Oh yeah, but we can still do this. We'll call this like A prime and B prime here. So now I'm going to have the inverse of the observability matrix transpose. So I'm just switching it with the X. Okay, here's another property that we're going to use here. If you have the inverse, if you take the transpose of the inverse of a matrix, that's the same as taking the inverse of the transpose. And I guess you could prove that because you could say like A times A inverse. We know that's the identity matrix. Like that's just the definition of an inverse. What if we took the transpose of this? So I know that above is true. If I take this, then I'll have the inverse of the, or the transpose of the identity matrix, but that's still the identity matrix. Okay, but now I could take this principle up above and apply it to this. And I would get, this is equal to A inverse transpose times A transpose is equal to I. So if A transpose times some other matrix is equal to the identity matrix, well, what's the definition of an inverse? The definition of an inverse of a matrix is if you multiply a matrix by its inverse, you get the identity. So this must be the inverse of A transpose. I think I did a convoluted proof of this. Anyways, the reason I want to do that is because I want to say that this transpose of the inverse of the observability is the same as the inverse of the transpose. And you'll see why. Because now this is going to look very much like the Ockerman formula up above for the control Ockerman formula. So let's see. So this was Y. This was X. All right, I'm just going to start plugging stuff in for this. So that is equal to 0, 1. So that's Y transpose. And then the observability matrix transposed looks like this. And then you have the inverse of it. And then the X matrix up above, if you transpose that, it would be A transpose squared minus 1.52 A transpose plus 0.67 times the identity matrix. So we have this formula. L transpose is equal to this stuff. And if I copy and paste the control, so I'll just copy that really quick. You see these look now like the same. So I think you use the numbers for gain there instead of L. Oh, okay, good. You're right. So 1.52, what do I need to use? Minus 0.42 and 0.3042. Minus 0.42 and 0.3042. Okay, but now this would let us use the, so in MATLAB we'll say L transpose is equal to Ocker of A transpose C transpose, and then whatever poles you picked for your estimator. Yes, that's right. Or yeah, you could say L to forget about this transpose thing. You could just take the transpose of this formula, and you do that by doing an apostrophe. Okay. How about we, so let's go back over to MATLAB. So we can run this really quick, and then we're gonna get into some simulation. Okay, let's talk about the estimator. So L, let's do this. This code that I'm building on, by the way, is a code that we started on April 16th, and we've kind of built on it ever since. So if you have that code, that's the one that I'm building on. So let's do this. A transpose, C transpose, and let's define beta star. I'll have to go back to this previous set. It was 0.21 plus 0.51 I and 0.21 minus 0.51 I. So let's just do that. Let's put beta star in here. And let's just run this code. Okay, it's generating some plots from before, and L is this. Wait, did I put a transpose on it? I need to put a transpose on this. So L is actually this. But wait. Is that the same thing we got? Oh my goodness. That's the same thing that we got with the other formula. So, the lesson is, you can use the Ocker command to get the estimator gain matrix as well as the control gain matrix. So when you're doing the homework or whatever, it's okay if you want to get your L matrix in 2 lines like this. You pick your target poles for the estimator, and then you get that matrix. And just to show you this is the point once again. This matrix represents the dynamics of your estimator. Place command would give us the same gains, right? I believe so. Place is another command that implements the Ackermann formula, but I think it does, yeah. Place, so the Ocker command only works for 1 input, 1 output systems, whereas place works for multiple input, multiple output. So this is sufficient for now. So this is the dynamic, this is our system matrix for the estimator. If I take the eigenvalues of this, those should be equal to beta star. So that's the purpose. And you see the The eigenvalues of that are the same. Good. All right. Okay, let's start doing some simulation. Okay. What I want to do, I want to go back up to this. And I'm going to copy this. This was simulating the closed loop system, assuming that we had the system states X. So I'm just going to start with this. I'm going to copy it down here. And so now we're simulating the closed loop system, but we're making it a little more realistic. We're going to assume that we're using an estimator. So to physically imagine what's going on here, is this code something you would post or something we should have been writing along the way? It's something that we've been building along the way. And at the end of the lecture today, I can scroll from top to bottom in this code, so you can always come back to the video and write it yourself. But I won't post this one. So, okay, so the cart, it's starting pitch, the estimator, yeah. So it's pitched like 15 degrees, and so it's going to start falling over, but our controller is going to intervene, okay? And we're just going to simulate this for 20 time steps, where each time step is, what is it, a 20th of a second? So really, this is only going over 1 second of time when this pendulum starts to fall over. Okay, so this is our initial measurement from the rotary encoder. So we have some initial states, but we don't know what the true states are. So what I'm going to do is I'm going to make some new variables. We need some estimated states. X hat. I keep using the wrong comment symbol. Estimated states. Okay, so we'll call X the true states, and we don't know these. I'll explain more as we go. All right. We're also going to have Y hat. So I'm just initializing these variables right now. I'm making some placeholders. This is going to be our estimated output, which is the angle of the pendulum. So the way the estimator works is you're going to estimate what you think the measurement from your sensor is going to be. We'll call that the estimated output. And you compare it to what the sensor actually says. So this is our actual output. So this is our sensor measurement of the angle of the pendulum. Okay. Let's assume before this simulation starts that we have a very good idea of what the initial states are. So let's say our initial state estimate is actually equal to the true initial states. So let's just assume we have a good guess. And so I guess let's assume that our estimated sensor measurement is also dead on. So Y and Y hat are the same at the beginning. Now, when we define our control input, remember, we don't know the true states. So every time we define the control, we're going to have our gain matrix times our estimated states. Okay. Now let's get into the loop. Let's assume that this is what the system is actually doing. true system dynamics. But I'm running this in the simulation, but you have to put yourself, imagine you're in real life. You don't actually see this. What you see, let's move this up. What you see is the sensor measurement. And the sensor measurement is based on the states. It's a function of the states, but I never see this itself, okay? So let's just say that. Oh, wait, but I needed this line in front because this technically depends on my control input. So I should define my control input before I get this measurement. But this, once again, it's going to be a function of my estimated states. Okay. So we have to put our estimator equation in here. Let's put it right here. So we're running this estimator in parallel with the real system. And this is what we think the states are doing. So and this looks similar to the line above. X hat k minus 1 plus b times u k minus 1. So we're running the same model, assuming our model is good, but it's based on the estimated states. Okay, but we add this little extra piece, and this is the beauty of the estimator. It's going to use the L matrix that we just got, and it's going to multiply with our measurement error. So we take the difference between our estimated sensor measurement, so y hat, this is what we think the sensor would have given us, but it's going to be different from what the true sensor gave us at the last step, generally. So we take the L matrix times how much our prediction of what the sensor was going to tell us is off, and we add that to the model. Okay. And then once we have this estimate of our states, then that allows us to calculate the control input. That's what we're going to give to the system. And our sensor is going to be a function of the true states. Because remember, the sensor is mounted to the true system. So it makes sense that the true states are here. And then we also have our input. I think in our case, D is equal to 0, but I'm just putting it here to make it general. Okay, and what I'm going to do to make this a little more realistic, I'm going to add some noise to this sensor measurement. So if you use this rand in, it picks a random number from a normal distribution. So that's like a Gaussian noise, which is typical for a sensor. And I'm going to put some I'm going to make it kind of small. So what this does, it's going to add a small random number to whatever our sensor measurement is. And so this is what we actually see coming off the system. It's something that's based on the true states, but it's corrupted by some noise. And that's the best we ever get. We never see the true states. Okay. Is this all we need? Do I have everything right here? We update the system. We estimate the system. Is that considered white noise? Yes, it is. I mean, do we not use y hat? Oh, yes. Thank you, Mike. Okay, so this is what our actual sensor measurement tells us. Thank you, Mike and Kate. You guys are keeping me honest. Okay, so this is what we predict the measurement's going to be before we even look at it. And it's going to be this. But I put hat here. Because I don't know the true state. So I say like, this is what I think the sensor is going to give me. Like, this is my best estimate of the states. So I know this is the relationship between the output and the states. And I know what the control input is. Well, it's this based on my estimated states. Okay. Let's do this. Let's make some plots. I'm actually going to make... Let's start with... We'll do 2 plots right now. So we're going to plot what the control input does. We're going to plot the true measured output of the system, but I also want to plot our estimated output of the system. So how about we copy this? And let's put y hat. And I'll make this green. Green dots. Let's put a legend on here just so I can distinguish between the two. So we don't have to remember which ones. So this is our measured angle. Estimated measurement. So let's do y. And this is y hat. Is this going to work? I think it will. I believe in this process. Did we initialize everything? Okay, let's run it. Uh-oh. Guys, we have a problem. Something's going unstable. When this happens, those numbers are large. Did you see that? It's like 10 to the 11th. Something is going unstable here. Do you guys see something? X hat plus B plus L. Wait, should it have been minus L? Oh my goodness. Guys, this should be minus L. If you go back to... Wait. If you go back to our estimator... Wait! No, okay. Yeah. Minus L. That's why. Hidden back there, there's a minus sign. And we did not put that in the code. Minus. Boom. Let's run it again. Mine's still going kind of crazy. Mine too. This is still unstable. Let's take a peek. So this is definitely okay. X hat is A times the estimate plus B minus L times the measurement error. That looks okay. And then our control input is based on X hat. And then Y hat, C times X hat. That's correct. Plus D. You know what? I wonder... Do you think this noise... Okay, let's first... Because the noise is going to make this... It's going to make it harder on the... Looks like the L is after for loop. Where is L? L got distributed? L should be distributed. Like, it should be L times the... It should be L times the measurement error. Looks like the L is after for loop. Where's L? Wait, this is right, isn't it? Like, if I go back here, it should be L times the difference between y hat and y. You got rid of the noise and it worked. Okay, let's go here. And for now, let's get rid of noise. We have y hat is c hat. Okay. Okay. So this is good to know. This is good to know, by the way, that in real life you always have noise, and that if you have enough noise, it's definitely going to make... So let's just add like a little less noise. Because I want to show you that it's not going to look perfect. So now I'm just making the noise a little bit smaller. Let's see if it works now. Okay. So now it's not going unstable. Let's make it even a little smaller. Like, let's chop that in half again. Okay, so you can see, so and this is kind of what we saw with Project 1, right? Our controller didn't go perfectly to the reference. It kind of went there and then oscillated about it a little bit. You put rand, not rand in. Oh, good point, good point. Let's see. Okay. So going a little crazy. Okay. Do I have time? Mine looks like less of a mess with rand comparatively. It should be rand, like usually for sensors, it'll be this rand n. So it's like normally distributed. So rand is from a uniform distribution. So it's a little like, if you have, how do I say this? Like this is a uniform distribution. Like if you have a variable x, and this is the probability of x or something, like over a range, the probability for any given x is the same. But for, you know, we've all seen Gaussian, like the probability or whatever, it's more concentrated towards that center. So the uniform random noise, I think it kind of spreads out the noise a little bit more, whereas the uniform is a little tighter. I think we're running out of time for this animation. Could you show all the estimator code again? Mine is still unstable, not sure what I missed. Okay, let's do this. Instead of, so we'll finish up I'll minimize all these. We'll finish up the actual animation on Friday, but there's one other kind of disturbance that I want to show you here in addition to the noise. Easy 8, yours is still unstable. So I think first thing to check, make sure you have a minus sign in front of the L. Make sure you have a minus in front of the K. Make sure that you reduce the amount of noise because that'll throw it off. Make sure you have y hat minus y in here. My L was positive. Okay. Okay, good. Okay, here's another type of thing that can happen. So what I'm going to do is I'm going to simulate a cat coming in and whapping the pendulum. Let me show you what this disturbance is going to look like. You're gonna love it. Okay, let's define it right here. Cat. I'm gonna make a square. Did I make a time variable? Okay, I do have that. Okay, I think this will work. Just trust me on this for a second. Let's make this. Okay, 5 times this. This is gonna make a little boop, a little bop. You'll see what I mean. And then we're going to do minus 5 square times pi times t minus pi Here, let me show you what this looks like before we do it. Plot as a function of time, cat. Wait, where did it plot it? I really should make another figure first. Is this gonna work? Wait, that is not... Oh, no, this is okay. This is okay. Needs signal processing toolbox? Okay, basically all this does... You know what? A much easier way to do this. Here, so you don't need the signal processing toolbox to do this. Here, what we're going to do. What we're going to do. What we're going to do is if k equals 3. So at a random time step, the cat... if k equals 3... the cat is going to boop. And so we'll just make cat a random number, actually. So let's just suppress all of that earlier stuff, and let's make cat a random number. And I'm not sure what the right amplitude is going to be yet, but let's just put like 500. And so remember, u is the angular velocity of the motor that's driving a belt. So this cat is effectively bopping something and jarring the motor so that it has a different angular velocity for a certain step. And our estimator is not going to account for this because we have no way of modeling. Okay, let's have the cat whap it again at another random time. Really, we should put this inside the for loop so it always calculates a new random variable. Okay, and then other than these, let's do that. Or like 7 or something. I think I have to put double equals here. And then for all other values of k, let's assume that the cat is not involved. Okay, see what I did? We're just going to do it this way. Wait, why is it giving an error here? An end might be missing. But I have an end here, an end here. It's else if? Okay, okay. I think in Arduino land it's uncomment the cat. Okay, else if, not else. Okay, so we got to get rid of that space. Okay, so each time we go into the loop, at these special times, the cat is going to bop our system. And our estimator has no idea how to model that, so we just leave that the same. And let's remove any noise. Or I guess we can leave it. And I want to increase the length of this simulation a little bit so it has a little more time to recover. How about we do 40 steps instead of 20 steps? Give it a little more time. Maybe even 50. And here, when we plot our input, let's also plot looks great. Okay, let's run it. What's little n supposed to be? Wait, we need to include a plot of this cat variable. So, okay. Cat K. No. Because I want to be able to plot exactly what's happening here. Zeros, 1, n. Honestly, it seems to run better with the cat disturb. Wait, the cat helped? Are you serious? Okay, so all I'm doing right now is I want to be able to plot this disturbance. So throughout the loop, I mean, normally it's 0, but at step 3, we're going to assign it these variables. So now when I come down to plot, I should be able to plot what the cat did. Let's put cat. And let's put it in red. And let's, so you'll be able to see this now. We'll make a legend. We'll put control input. And then we'll put cat. Does it really run better with a disturbance? I don't want to believe that. Wait. Oh, okay. I see what happened. So now I can't, because I made cat a vector, wherever I add cat, I have to make sure that I just add the correct index, not the whole vector. All right, let's run this. Let's run this again. Another error. Cat. Incorrect number of inputs for property value pairs. Wait. What's the size of my cat? What's the size of you, though? Let's go to that line. T, U, T, cat. Wait, do you guys know why it's giving me an error here? Maybe stairs only... Oh! Oh, you're right. You can only do... Okay, so what we're going to do... I have to cut this out. Let's put it down here really quick. Or rather... Let's just do a hold on. And then let's copy this. And now we're going to put this in here. Okay, so stairs only likes to do one line at a time. So that's why we couldn't double up. So instead we plot, we hold, we plot, turn off the hold, whatever. Okay, let's run it. Okay. Oh, this is interesting. This is interesting. So let's make this a little bigger. Because you see the control system react. So the cat whaps our pendulum right here. The next step, and I mean, you see the dynamics, the angle went down to like minus 45 degrees or something. So our controller had to really compensate in the next step to recover. And then it kind of overshoots again. And then the cat does a little boop this time. So the reaction to that is a little less severe. But this is cool how you see... Can you show me the for loop one more time, please? Yes. How about we get rid of this noise too? Because I want to show you that if the model, if you don't have noise, then the predicted measurement should converge to the true measurement eventually. Holy Toledo, Batman, that response is huge still. Yeah. I'm going to get rid of the noise and run this again. So you see that the green, which is the estimated measurement, converges to the true eventually. And actually, we should have showed this first before we introduce noise, because I want to convince you that the estimator equation, if your model is perfect, it does converge to a true value at some point. Now, these numbers, the control input, this is large. Like, this is 10 to the 4th. But remember, the units of this is the angular velocity of the motor in degrees per second. So, like, up here at its fastest, this is what, maybe like 35,000 degrees per second. So what is this? 35,123 divided by 360. That's 97 revolutions per second, which is still really fast. That's 5,000 RPM. But with this cart pendulum system, you can play with the gear ratio of the motor, so it might not have to spin quite so fast. Let's go back to the code. So we're I guess it's only doing it for 0.05, which is, we can talk more about that. We need to hook up a ZR1 to the belt. Yes. So, okay, for your homework 5, you need to make a loop, something like this. And I tell you what the initial conditions should be and so on. But it'll be a little more straightforward than this in the homework because we're not going to have this weird cat function. But the general structure of the loop should be something like this. Estimated states, control input, estimated measurement. And you kind of run with that. Man, we're getting close to the finish line. So homework 5, at this point, you'll be able to finish that. And definitely ask any questions, whatever you're confused with, reach out to me, reach out to our TA Nikta. And then after homework 5, we're going to have our project, which I'm just in the final parts of tweaking. The project 2 is going to involve this kind of stuff as well. But what I'm thinking of making project 2, I had a different idea at first, but I want to apply this kind of control to that 6-volt motor. Antonio says, are we going to animate? Yes, we'll still do an animation because this is going to be, you want to see this. You want to be able to see this. Can we just use MATLAB to calculate K and L? You can use MATLAB to calculate K and L. That's okay. Project 2 is going to be a little shorter than Project 1, I think. Because some of that has to do with the state space process as well. It's faster. Can we do yes. We'll do a slow code scroll through as I talk. So we'll start at the top. So yeah, project number 2, I want it to be designing a controller for that 6-volt motor that we did for project 1. For project 1, we did the root locus design method. So I'm thinking of project 2 approaching the same control problem, but use these techniques. And I think that'll be really valuable because you'll be able to compare and contrast your experience as the control designer for that. And you'll be, and so I'll ask you questions in the project too, like, how does this compare to your experience for, hey, see you later, Kate. How does this compare to the root locus method and that design process? What is easier? What's more difficult? And I think a lot of it will be a little more straightforward. But in order to do that, is Ekf supposed to be better than a simple Leunberger? Yes. So Ekf is the extended Kalman filter. A Kalman filter is certainly going to be better than a simple Leunberger because it explicitly accounts for sensor noise and modeling uncertainty. The Leunberger kind of assumes that the model is perfect. I mean, it doesn't really, but it doesn't really account for everything. Oh, so what I was saying is we need to talk about, I'm going to scoot this code over so you can see. We need to talk about how you can use an integrator in state space methods. So on Friday, we'll do this animation and we will start talking about how you add an integrator because you need that to follow a reference signal using state space control. Right now, the reference is just 0. We're trying to balance. But if you're trying to follow an arbitrary reference signal, You need an integrator. Okay, so that's it. That's the bottom. We did the slow scroll. Amin says, can we use EKF for linear systems? It would kind of be pointless because the EKF is just a linearized Kalman filter. If you have a linear system, you should just use a Kalman filter. Because linearizing a linear system gives you back the same system. So an EKF for a linear system would be the exact same as a linear system. All right, everybody. Thanks for hanging with me. Hey, see you, Pika. You guys hang in there. We're at the very, very end. I know you're wrapping up a lot of different stuff. You can do it. See you later, Amin. See you, Mike. See you, Chinghan. Any news on when Project 1 grades will be done? It's still a little more time. Sorry about the delay on that. Hey, see you later, Brandon. See you, Jimolino. See you, Benny. When do I think Project 2 will be due? I think I'm going to be a little bit flexible and push the deadline. Like, it's not going to be due at the end of next week. I think I'll give a little bit extra time. God Woe says, hi, I'm not your student, just a regular developer who stumbled on this stream. Do I get anything out of watching your lectures without much physics background? I would say at this point so this one is digital control systems, and we're mainly using discrete time dynamics equations. I think if you don't have much background, if you go back to the beginning of the semester, you'll still be able to catch up. I mean, if you have experience with some like linear system dynamics, that helps a lot. A lot of students in this class are in a mechanical engineering program. They're seniors who have taken a couple dynamics courses. But the stuff from the beginning of the semester is on YouTube. So I think you could definitely catch up. Weiss says, are there going to be any other homeworks than the one due next Monday? No. So homework 5 is the last homework. Hey, you're welcome, Godwoe. No, just this homework, and then that last project, and that's it. You're welcome. All right, everybody. Wait, Pika says, I have more assignments due than there are days left in the semester? Jeez. You hang in there, Pika. Holy cow. Oh, man. Everybody hang in there. All right. Well, you guys have a great rest of your Wednesday. See you again on Friday. Always a pleasure.